Hello and welcome. Today's video is going to talk about energy. We've already talked about work and power, so you've already learned about those. Work is the amount of force you're applying while something has a displacement, so either to make it have that displacement or to stop it from moving. It can also be defined in terms of energy. You can say that it's the amount of energy you put into the system or the amount of energy you took out of the system. Well, energy is the ability to do that work. It's the ability to cause something to have a displacement or to stop something from having a displacement. Slow it down, bring it to a stop, speed it up. So, since work has the units of joules, energy also has the units of joules. They're very tied together, and we're going to learn an equation towards the end of this that shows you that work and energy are related. So there's two main categories of energy that we're going to deal with. We only deal with mechanical energy. We're not going to deal with things like thermal energy or nuclear energy, anything like that. We're just going to deal with mechanical, which we abbreviate as ME. So there's kinetic energy, the energy of motion, and the equation for that is KE equals 1/2 times the mass times the speed squared. So 1/2 mv squared gives you the kinetic energy of the system. Then there's potential energy. This is the energy stored in the object, so its ability to do something because it's going to fall or because it's going to have a spring acting on it, something like that. So it's stored energy due to its position. And the one that we're going to deal with the most is gravitational. This is the stored energy due to a height. So PE is what we abbreviate for potential energy, equals mass times gravity, 9.81, times the height. Or if you're on a different planet, that g could change to whatever acceleration is on that planet. And we have elastic, which is from springs. So stored energy due to the elongation of a spring. And we abbreviate that again as PE, and it's 1/2 times K. K is the spring constant for the spring. This is any kind of spring will have its own constant. So each spring has its own K value, just like friction has as every surface has its own coefficient. This is kind of like a coefficient for a spring. And it's usually measured in newtons per meter. And then X is how much that spring is stretched or compressed from its starting position. And it's usually measured in meters. The X and the K have to match. So if K is newtons per meter, X should be in meters. If K is newtons per centimeter, X should be in centimeters. And then the X is squared. Because we have two potential energies, I usually write it as PEG with a small g next to it, and then PE spring or PES, the small s next to it. Some people you'll also see write GPE for gravitational potential energy, and SPE, spring potential energy, or EPE, elastic potential energy. And even weirder, sometimes people write KE as capital K, and then PE as just a capital U. I have no idea why anybody writes it as capital U, but you will see that sometimes in textbooks or online. So just keep that in mind. If they're writing K and U, it's kinetic energy, potential energy. Also, mechanical energy, sometimes they'll write mechanical energy, ME, as the total energy of the system. Sometimes they'll write capital TE as total energy of the system. Could be either one. Total energy is any combination of these. So you could have something moving and have a height. You could have something moving with a height and a spring involved. So you'd have all three of these combined. You could have just one of them. So at any point in time, an object can have one or more of these or none of them. You could have no energy. These are some of the types of energy that we're not going to deal with. So nuclear, electrical, chemical, thermal, light. You've already dealt with a little bit of it, some of these in chemistry. We don't deal with these in this level of the course. All right, so let's go through some scenarios and try and figure out what kind of energy is in each situation. So dog is running on the ground. I'm going to go through these and just pause the video and think of the answer yourself and see if you get it right. So dog runs on the ground. Since it's got no height and it's moving, it has just kinetic energy. An airplane flying while high above the ground. Airplane's flying, so it's moving, so it has KE, but it's also above the ground. It has a height, so it has PE, gravity. I would say PE, gravity, not just PE. Book held 4 meters above a desktop, so it's not moving, has no KE. There's no spring involved, so no PE spring, but there is a height, so there's PE gravity. A loaded dart gun with a compressed spring mechanism. Well, if this has a spring involved, it's not moving, and there's no height, so it's just PE spring. If you were running with that, then it would have a height because you're holding it above the ground. So it has both PE spring and PE gravity, and you're moving because you're running, so it'd have KE as well. So you could have all three. So what you're asking yourself here is the object moving? If your answer is yes, it has KE. Does the object have a height? If the answer is yes, it has PE gravity. Does the object have a spring? If the answer is yes, it has PE spring. If it has all three, you add them all up. If it has none, then nothing, zero energy. Or OJ. So total mechanical energy is you're adding up all of the kinetic and potential energies, just like I was just saying. So let's try that out. So a 2 kilogram ball is thrown with a speed of 4 meters per second at a height of 5 meters above the ground. How much mechanical energy does the ball have? So we're going to say ME equals all the energies added up. So this has a height and a speed, but no spring. So we're saying yes to PE gravity, because that's the height, and to KE, because it has a speed. Oh, of course that would happen. Hold on a second. KE. There we go. And let's erase some of this nonsense here. Let's just write that over again. All right, sorry about that. So now we're going to replace both of these with their formulas. We've got mgh plus 1/2 mv squared. Mass is 2 times 9.81 times the height is 5 plus half times 2 is the mass times the speed is 4 squared. I can't fit the square in there. And then we just plug it all in. And we get 114.1 joules. So there we go. That's our total energy. You could also find these separately and just add them up, but I think it's just easier plugging them all in one time. And here's just a slightly different way of writing all that out. Now, energy can change forms. You can't lose or gain energy, but you can change its form, and that happens very easily. So we have light energy, or energy from light, turns into chemical energy through plants. Photosynthesis. You have electrical energy that can turn into heat. You have chemical energy from our bodies, or things that we eat, can be turned into mechanical from our bodies. Chemical energy from gas can turn into mechanical from a car. Or you can have light turn into mechanical. So on and so forth. Whoops. So there's lots of different ways that energy can transform, and it tries to do so very easily. One of the laws of physics is that energy cannot be created or destroyed. So it's called the law of conservation of energy. So energy can never be created or destroyed. Whatever the universe had at the very start, it still has today. There is no more and no less. It can be changed between energy and mass, and the famous equation for that is E equals mc squared. This actually shows us the energy can change between energy and mass, but that's only under very extreme circumstances, nothing that we're gonna ever deal with in this class. So, for all intents and purposes, energy can never be created or destroyed. It only changes forms. So it can be hard to keep track of what form energy is turned into, but if you keep track of all of the different forms that it turns into, you can keep track of all the energy you started with and ended up with, and it will never have gained or lost energy anywhere within a system, or within the universe, really. So, if we define the system correctly, energy remains constant. So here we have a skier on a slope, and you can see at each point, even though the energy might change values from kinetic to potential, the total always remains the same exact amount. As long as there's no work done on the system or taken out of the system, the energy for the system remains the same. So here the skier is not moving, but it has a height. So you have all potential energy. Then a little ways down the slope, the potential energy has gone down because he's lost height, but the kinetic energy has gone up, so it's gained some speed. And that just changes back and forth throughout the whole path of the skier. This makes it pretty easy to solve a lot of different problems, especially things like projectiles. It's another way for us to tackle those types of problems and make them slightly easier for us. So if we drop a ball, it starts with all potential energy, it has height, but it's not moving yet, because dropped means VI is 0. As it falls, it's losing potential energy, it's losing height, but that energy is turning into kinetic energy, it gains speed. So at the very bottom, all of that potential energy is turned into kinetic energy. So if it starts with 5,000 joules of potential energy at the top, at the bottom, it has 5,000 joules of energy, kinetic energy. If we toss it upwards, the same thing happens. So as it's going up, it's gaining height and losing speed. So at the highest point, all of the kinetic energy it started with is turned into potential energy. So all the Ke here turns into potential up here, and then back down turns into kinetic energy at the bottom, and no Pe. So it can transform back and forth. So when it leaves his hand, it's all kinetic, if you don't care about the height between him and the ground. One of the other things about energy is we always define the lowest point in the object's path. So the lowest point in the problem is always our 0 height. It doesn't even matter if it goes underground. The lowest point it gets to is 0 height. That's going to matter when you design your own roller coaster. You can make a roller coaster that goes underground, but you have to deal with the lowest point in its path being 0 height, because you can't have energy, negative energy. When it reaches a max height, you have potential energy. When it comes back to his hand, kinetic energy. All right, this video is going to leave off here. You should try 2 worksheets assigned, and then the next video will go over how to deal with more complex problems.